Professor Lai from the JiunCheng University. He's going to talk about maintenance conjecture.
Yeah, this is the motivation of the talk. Thank you for the opportunity to speak here again. We had the fish country, so very nice. So the motivation of this series of seminars is maintenance conjecture. So, and then we try to, out of this conjecture, to extract geometric informations on this kind of variety. So, what kind of variety we're going to study? Smooth projective variety. We assume minus kx is ample, so meaning it's final, and in this case, it's expected it has many rational points if it's defined over a certain number of them. So in this case, if you fix an ample line bundle, so you can thinking about you have an embedding projective space, then you can count, you can define height on this projective embedding, meaning the point like Q rational point, so you can ask the absolute value of this rational point to be how big. Okay, so if it, for this fixed embedding, you fix a height, you count how many rational points you have with respect to given height. Then it is expected, there's one conjecture saying, when the height is growing, you expect the number of rational points has this asymptotic behavior. Okay, so when B grows, there is a constant coming from the variety and also ample line bundle L. Also, the growth order is controlled by two constants. The first one is A, the second one is B. So I'll give you the definition again later. So the original conjecture says, well, it's not the whole variety you are counting the rational point. Actually, you will find, you want to find an open subset such that over this open subset, when you count the rational point, well, sometimes maybe you have to take the finite extension so that you really have a rational point. But then within this open set, the behavior is like this. Okay. Now there are examples. If you don't take the open set, you get a problem. So maybe I should start with the example. So suppose, I think I told you one example before. Let me just write down. There are examples. Y such that the number of rational points of UYY B is so suppose this is like B to the 8th order. YL bigger than X. So then you can easily find examples where if you count the number of rational points on a subvariety, actually it contributes more. Okay? So in this case, if you want the conjecture to be true, you need to exclude this kind of subvariety. Okay? So with Y from this conjecture. So that's why you don't take the whole variety, but you take the whole set. The first problem is, well, this kind of subvariety can be many. Okay, so the question is, how many Y's need to be removed? Okay, so that's the first theorem. It's the main theorem of my talk. So let me state it. So suppose X is a smooth projective. This time is defined over C. So if you are not in this series of talk, the motivating problem is from number theory. But the geometry we talk about is always over C, over a field of characteristic zero. Okay? So it's kind of the problem geometry motivated by number theory problem. And then L is ample. So let me remind you what AXL is. This is the inf T such that Kx plus TL is a pseudo-effective. So A number is just a pseudo-effective threshold. So you should think about this time Kx is not pseudo-effective. So this A is a positive number. Kx pseudo-effective and Ax positive. Okay. So in this situation, then the statement is there exists a subset of X, which is a countable union of a proper closed set of X. I can put subvariety, it's the same, such that for all subvariety which contradict the harmonics condition, so which has a bigger Rosse order, actually Y is inside D. Okay, so the good thing is now you don't see that this kind of Y covers the whole variety. So it's possible to find out not an open set, but to find out a very general open, not very general, complement of countable union of closed subset. Okay, so this is the first step. Now let me make a remark. Later on, we will study, we will consider X, I think it's unirule, or probably even a final case where D can be taken as a finite union. So this is more likely the situation we want. Okay, so really you can find an open set in on this situation. So you only want to remove a finite many is unexpected. But now for the general situation, if I don't put any geometry on X, okay, so it's close to what we want already. So you only need to remove countable in that.
So here doesn't say that P is proper.
But in this case, then it is. If so, if it's a smooth projective variety, it cannot be written as a countable union of subvarieties. The content will not equal X. This is one of the bare category theorem. Okay, so a subset, a closed set, compact space is not a countable union. That's a box. So the proof of this theorem is rather easy. So I think I can finish in 20 minutes. Okay. So before I give you a proof, let me mention what I want. So this A is defined in terms of the pseudo-effective threshold. So we need to have some condition to check if it's pseudo-effective. So this is a well-known BDTP. So X is a smooth projective. We have the pseudo-effective cone. But we also have the other things, the dual of the pseudo-effective cone. Theorem is or maybe not, let me not put it this way. So what is a pseudo-effective cone? Well, it's actually the dual of the movable curves. Okay, so let me explain the notation. So X is generated by movable curves. Okay, so what do we mean by movable curves? So meaning, should say this is a curve class. So everything is in the numerical class of one-dimensional cycle. So this is inside M1x. I think this closure is correct. Movable means that there exists a family of this curve such that union CT is 4x. So, and of course the CT has the class C. Is that okay? So that's what we mean the movable curve, movable family. So the curve moves and then covers the over x. On the other hand, this is also can be described. It's generated by curve where the normal bundle of C inside X is net. So here the normal bundle is defined to be the dual of usual column motion. So we have description of this column of movable curves. Okay. And the third description is actually you look the following things. So mu lower star h1 intersection hn minus 1. Okay, so n is the dimension. And the mu is directional transform. Okay, where hi are general endpoint divisors on x delta. Sorry, a little bit. Okay, so this is like really you can see the curve is moving because you are taking the general endpoint divisors on x delta. So it cuts the covering family of curves, then you push forward. Okay, so that's the column of is that okay? So in order to check something is pseudo-effective, what you want to do is you choose any family of movable curves, and you look at if it's in dual. So dual means that the linear functional is not negative.
So in that description, the mu can be any directional morphism?
Yeah, smooth bidirectional. So this is a smooth. Sorry, is this clear? Okay, so you take any smooth model over bidirectional smooth model over X. Take hyperplane sections to cut to a curve and push forward. So hence this is saying L is pseudo-effective if only if L dot C is greater than 0 or OC inside. Okay, so that's the PDTP. So now prove my theorem. So let me start. So you want to say you want to exclude this kind of subvarieties which are bigger with a bigger pseudo-effective threshold. So first step is you consider all subvarieties. So all subvarieties of X, we're going to interpret this in terms of the family of varieties. So this is actually, you can think of that as a union. Okay. I can use either Hilbert scheme or chop variety. So this is a family of subvarieties. Okay, and here, if I talk about all subvarieties, then this H is not Noetherian. Okay, it's a counterbody union depending on your Hilbert polynomial. So if I'm thinking about a Hilbert polynomial, actually this is a disjoint union of HP, and this is a disjoint UP. UP is my universal family, and this is a Hilbert scheme. P is a Hilbert polynomial. And the key thing is that this is countable union. So I only have to check on each Hilbert scheme. I exclude only countable many guys. Okay, so the statement I want is the subvarieties I'm gonna remove is a countable union. So in each of these Hilbert scheme, I'm gonna remove countably many guys. And since I have a countably disjoint union of Hilbert schemes, in total I remove at most countable many. Is this clear?
Sorry, I don't understand the subscript.
P is the Hilbert scheme of Hilbert conductor. Is this okay? So this is a perimeter space of the subvarieties. UP is the universal family, so if you pick up a point, then the UP meaning is just
union over all the Hilbert polynomials.
yeah, you consider all possible Hilbert polynomials. Because at the beginning I don't know which one to exclude, so I consider all possible subvarieties. Okay, and then I try to see which one I have to remove.
When you say it is countable union, then you have only countably many Hilbert schemes?
Yeah, here we only have countable many Hilbert scheme because polynomials is countable union. It's an integer coefficient.
Integral coefficients.
Yeah, integral coefficients. Yeah. So the claim is on each UP over HT. So remember there is a tautology map from the family of varieties to X. Subvariety is with A, Y, shouldn't say this. A general member. General phi y equal to let me call this map pi is map mu. So mu of y, if I pick a point h, y h, okay, so this is a fiber. If I take a general member of this family, I take its image inside X, then this variety satisfies the AYL less or equal to X. Okay. So this tells you the things you want to exclude is outside and offset. General meaning that in the content set of HT. Is this okay?
What is like
Pi. Is it clear? So each family only, so a big portion of this family actually satisfies this inequality we want. The reversing inequality only happens only outside this subset. Okay, so that's a countable. If you look at the image, that's not set yet. From this, we can conclude it's a problem.
you mean for general H?
Look at general H, look at the fiber. Fiber means a subvariety of X, right? So you look at its image, then this variety has this part. So the one we expect, not the one we don't expect. Oh, so here I have to put the assumption dominant. So if the family is dominant, then this is true. So let me show you how do I conclude. How do I conclude from this claim? Okay. So if UP over HP dominant X, sorry, not dominant X, not dominant this is pi. So that means pi of UP is properly inside X, right? This is proper closed subset. So I can just put this whole thing inside my B. So I just exclude this family. Okay, so I don't worry about this type of family. Now if UP, HP, which dominant X, okay, then I know a general member of this satisfy this satisfy this good inequality. So subvarieties to exclude is given by certain. You can look at another subscheme. Okay, this is a subscheme, closed subscheme. And look at UP prime. Okay, so this means the restricted family, right? So the subvarieties you want to exclude, you only need to restrict to a smaller family. Okay, so outside the open set. Do you understand what I'm saying here at the point? Okay, so if this general member is inside some open set of HP, let me call this, I don't have too many symbols. So if this is called U, P. So this HP prime is just HP minus.
When you move in the family, is this A, Y, L continuous or upper semi-continuous or any?
We don't know. If it's moving along Y, I don't know. But if it's moving along L, it is.
But you are moving along Y, right?
Yeah, we are moving along Y.
So, I mean, you have a family, but and for each member YT, you have a YTL, right?
Yes.
And then, if you know nothing about how the
If you know the invariance of very general, I think, yeah, you are right. Because AYL is defined by pseudo-effective threshold, right? You look at the Kx plus AL, you look at if polar dimension is non-negative or not.
AYT means you do the same thing on Y, right?
Yeah, Y. So you retrieve Y
So
over to Y.
Yeah, I don't see why it should be upper semi-continuous or lower semi-continuous or any. When you vary this Y, then it seems like a very just some random rational number.
Yeah, priority. I don't see why it has semi-continuous. You can see, yeah. I'll get to that point. Yeah, we will see why is for general member. I have to pick it. So let me finish the argument here. So now for the varieties you want to exclude, it's outside this open set. So you look at this outside the open set, this smaller family, and you look at still the tautological map, pi to x. So pi prime to x. So if this pi prime is not dominant, you are okay. If pi prime is dominant, then you do the same argument again. So you are doing the Noetherian induction. So pi Noetherian. Consider pi prime and use Noetherian induction. Okay, so the subvarieties you're going to remove actually is only inside the countable unit of the properly closed subset. Is that okay? So if you have a family dominant X, most of the members is good. So only outside only our closed subset is not good. So you remove those. So let me give you a lemma. Saying how do I consider this family? Okay, so if you have a family, let me use the same notation with H. So I will assume this is normal projective. I can assume this is a smooth projective. So the reason is in this construction you can always take the normalization and take the smooth family, smooth modification. So the proof still goes through. So it is okay. Then if I take a general point and look at general fiber, so for F is general fiber, the map, which from the cone of curves to cone of the whole family, actually maps the movable curve to movable curve. That's a statement. Okay, so the movable curve of the fiber is actually the movable curve of the whole family. So how do I use this lemma? So it's very easy to conclude from this lemma that the general member satisfy this inequality. Okay, so proof of the claim. So the idea is this: you have this family U over H, which I can assume this is smooth, this is smooth.
What is N1U?
What?
N1U.
Oh, U is a projective, smooth projective variety. So you just look at a cone, numerical cone of the curves. Cone of the numerical class of one
The
cycle.
U is just the universal family over H. Right?
Yeah, in application I'm thinking about the universal family. But this H is Hilbert scheme, so it's projective. And this U is projective. You can take a smooth model of U. That's what we're gonna apply to. I'm abuse notation, so probably not use U. It's easier. This is even more general. So if this is a X W over Z, let's say. So I have a map family, which is this is proper. Okay. And I have a general fiber, then the map from the numerical class of fibers. One cycle is on the fibers. There's a natural map to this uplift, but then you do a map to the movable cone of F to movable cone of W. Is that okay? That's a claim. So then with this lemma, so start with one of my Hilbert scheme. Okay. And each Hilbert scheme may be not irreducible, so you can replace it by one of the components. And that component may be not normal, so you can replace by the reduced part of the component, and you can take a normalization. So you can assume the base is normal. And then for the family, which is proper, you just take a resolution. Is that okay? So we can assume this case after H reduced, taking component. The result is then we have the nav curves maps to the nav curve. Yeah, the movable curve maps to the movable. Let's see. So after for this Hilbert scheme, we take a reduced part, take a component and the normalization.
So do you get a variety after such reduction?
Yeah.
Is that
Yeah, right. You take a component and reduce part. So let's say irreducible, reduced. And if you like normal, you do normalization. Or the other way around. You can always
I
take.
mean financial generation, I mean the
Yeah, Hilbert scheme is already Noetherian. If you fix it, so this is Noetherian. Proper. Right? So you can also make it like this. And the U you can take U prime, this is smooth model. Smooth model. Just take a resolution. Okay? So we are in Paris 0. Okay. So we can assume this whole thing, so let me put it this way. So this U prime over H is where we apply the lemma. So there's this induced topological map to X. So originally I used pi. Let me use pi prime again, sorry. Okay? So U prime over H goes to pi prime is the family I'm considering. So now what else you can do? So also take one more step. So for you now fix a general point H, general. And then there you have the YP, which is general, right? And then on U prime there is this YP prime. So here we have YP prime, which goes to YP, goes to this point. Oh, I'm using H. H. Okay. And the image inside X is Y. So this is Y. This pi over YH is Y prime Y. Okay, so that's the subvariety, a general member. So in this case, I want to compute the pseudo-effective threshold. So in order to do that, I first of all cut down the dimensions so that this is generally finite. I want to cut down the U prime so that this map is in the same dimension. Okay, so this dimension. So it's easy. So now taking hyperplanes containing H on the Hilbert scheme H. Okay? So if this dimension is 3, this dimension is 10, and this family has a relative dimension 12. So what you do is that you take the hyperplane section passing through the point, make the base one-dimensional. And because fiber is two-dimensional, so the whole family is going to be three-dimensional. Okay? So this is going to be dominant. So that's all what I'm doing here. Okay, so such that T, I'm using H, restrict to T inside H. The family here, U and U prime T, vector to X. This is again let me denote by pi prime if you like with T. This is dominant. Okay, but still my YP is inside. YH generic finite because they have the same dimension. So the ending argument is just computing the pseudo-effective threshold. So now let me write down the computation. Okay, so if I consider ky prime plus the xy, the number defined on x, this y prime means h. And then there's this pullback guy, L on y, intersecting C. So this C is inside the movable curve of the fiber. Okay, so I mean the dominating family. In order to check if this is a pseudo-effective or not, start with this line bound or intersect to the movable curve. Is that okay? So this is the line bound. And one, YH1. So the goal is to show this is non-negative. If this is non-negative, the whole thing is pseudo-effective. So with this number is pseudo-effective, means this number is too much. So I have XL bigger or equal to AYL. Is that okay? So that's the computation. So now you just compute. So this is actually cheap. So this KYH is coming from the junction, so I have to use the junction. So KYH prime is the KU prime T plus to restrict to YH prime. plus this divisor. Right? But this is a generic finite family. X is smooth, so we have the KUT prime is actually the pullback of KX plus some effective divisor. This is effective verification divisor. So the computation is this is actually the KX plus AXL. The whole thing restrict to YH prime plus E restrict to YH prime. Whole thing intersect with C. Okay, so this is by junction. And this is a movable curve. And this is an effective divisor, so the contribution is non-negative. Right? So this is greater or equal to KX plus AXL plus L intersect with pi prime H lower star C. Okay. And now because I started with a movable curve, the image is in the movable curve of X. I think that's my claim. So where do I start? Oh yeah. So here if I start with a fiber, right? So then the image inside the family UT is originally the movable UT. So somewhere, I think here, this is inside the movable UT. Okay. So if this is a movable curve in UT, maybe I don't even need to do this part. So this is nothing. Is that okay? Is that clear what I'm saying? So I use the lemma here. So only when you have a movable curve in your intersecting with the pseudo-effective divisor, you know it's not that. Question? Yeah. So now to prove the lemma. No question? So to prove the lemma, well, I'm using much more time. The proof of the lemma is easy. So I start with a curve C inside E F. So originally this is a curve plus. I should not say this. The movable cone of curves of fiber F is generated by covering family of curve C. And also I said this is generated by C with net normal bundle, right? So I only need to take one curve of this net normal bundle and check if this curve normal bundle inside W is still net or not. Check. Net curve of C inside X is still net. Yeah. So this will imply C is inside the movable curve. W. Is this clear? Right? So this is by the description of the movable cone of movable curve. But how do you compute the normal bundle of curve inside W? There is the sequence of normal shifts, normal bundles. There's C inside F. There's a C inside X. Then there's a F inside X. There's two C. W. Right? And this guy is net. This F, because it's a general member, general fiber, so this is actually all F to set up power. Is that okay? The fiber has trivial normal bundle, so this is also normal. This is also net. So extension of net bundle is net. So the lemma is actually a true number. Is that okay? So that finished the proof of my main theory. Now let me finish with an example. Where we can really find out a variety, and the subvariety with bigger A is actually a lot. So I start with X. This is a K3 over C, or actually over algebraic any code or any K equal to K bar. Not necessary over characteristic 0. So our main conjecture says that on this K3 surface, smooth, there exist infinitely many rational curves on X. That's a conjecture, it's not known. So the cone of a K3 surface is classified by JiunCheng. You have a finite list, it's either finite individual or it can be round cone, and most of the time it's generated by another -2 curves. Okay? But that's a curve class. To see if you can really find out rational curve is not easy. So it's a lot of people's work to figure out that in many K3 surfaces you really find out one rational curve and then find out many rational curves. So there's a theorem presented by JiunCheng and also Christian Lai. I don't know how to read it. This is 2012. Okay. So if the Picard number of X is odd, then conjecture is true. Okay. So now we have many K3 surfaces with these rational curves. So what do we do? Start with any n-point line bundle. You compute the a-excceptional. Now kx is trivial, right? So you start with any n-point line bundle. You don't have to put any positive coefficient. So this is 0. Okay. But when you restrict to any p1, so this C, the normalization is p1. You look at the restriction to C. Well, the degree of canonical is -2. So in order to make the degree greater than 0, you need to add 2 over degree of L on C. This is possible. Is that okay? So you have a lot of rational curve where the A is bigger than the A on X. So it's countable limit. So that's it. So I'll stop here.
Any questions or comments?
So this
C is one of these rational curves. So think about P1. So if on P1 you have an n-point line bundle, and the pseudo effective is -2 plus TL greater or equal to 0. Right? So T is greater or equal to 2 over. So because L is ample, this degree is always positive. So whole thing is positive.
So these kind of curves that are only countably.
Yeah, so because by what we're talking about, the subvarieties is in this countable effect. So in the curve class, they are in the same class with the same effect. So at most. So but the real thing, the key thing is that really you can find out this curve geometric. So you really have this kind of examples. And another remark in the Martin conjecture is if you are defined over number field, then removing the countably union of subvarieties empty state. Because subvarieties at most is countable in many ways. If it's defined number field. So the main theorem really makes sense only in zero characteristic or field which is uncounted.
So how do you the assumption become number one.
Oh,
Become
here?
other, yes.
Okay, so this is a deep theorem. So here, in order to, I can talk about the proof. Okay. So the reason is that in order to create, how do you create one rational curve on a K3 surface? What they do is that I think I can erase this. This is the idea. The existence of P1 on X. Okay. You start with S, you deform it to S0, which is a spatial K3. And then you can find out a rational curve there. Okay? So how do you find out a rational curve here? You start with an n-point line bundle. So this is also deformed. And you check in this linear system. You can find out a member which actually is a sum of P1s. Okay. I'm abusing the notation. This P1 is not the smooth P1. It can be the normal P1. Okay? But I just put this way. Okay? So usually in n-point divisor, in a linear system, you have to generate a member, not necessarily the sum of P1s. But first of all, they find out spatial surface where these guys are sum of P1s. You have to do some computation, but then you deform back. You get a P1 truly rational. Now, how do you find out many P1s? Next step is many P1s. So what they do is that they do mod P reduction. So this S, you can think about it's defined over some integral model, integral base. So this S is a projective subvariety, a projective variety. So the defining equation has finite coefficients. We collect the coefficients. So you think about your variety is defined over this ring of coefficients. Okay, so this is a Z of coefficients. So you take the spec. So this is a usual reduction trick. Then you can mod P. Because you take any maximal ideal in here, if you do reduction mod P, you get the characteristic P sub. Okay? So you get P. So you have many mod P reduction. So now the point is that if S has the key is after mod P reduction, the Picard number is even. This is weird. So even you start with Picard number 1, after mod P reduction, this guy can must have even Picard number. So meaning over positive heuristic, you have more line bundles. And each line bundles, you do similar trick to produce a true rational curve. And this true rational curve should not come from S directly. But you can try to find out a way to deform it back to S. And that gives you infinite P1s. Is that okay? So that's the main work of JiunCheng and Li. This is the invention. Okay, so I'll not explain it. So this is the invention. Any questions?
Yeah, let's say it's